Hello students. Now in this video we are going to learn another topic which is about linear stability analysis. This also deals with the phase portraits for phase curves, how you plot phase curves of certain systems. Now you have learned what a conservative system is, and for plotting a phase portrait for conservative system is quite easy. But then when you consider non-conservative system, it becomes difficult to construct phase portraits. For constructing that, you should have explicit solutions or very well defined solutions for the equations of motion. But then, what you can possibly do is construct or about the equilibrium point, which is referred here as fixed point or equilibrium point. So you find the equilibrium point corresponding to that particular system. So equilibrium points, which we mean to say that they are points where the system will stay forever. Unless you give any kind of a perturbation, the system will remain in that particular state for a long time. So that is called as the equilibrium point. And this point is also referred as fixed point or critical point here. Fixed point or critical point, they all are the same. Okay, so what you can do for a non-conservative system is you can find out such a equilibrium point and then you try to draw the phase curves in their neighborhoods. So that will be an easy way to find draw phase curves for a non-conservative system. So now we are going to learn about the plotting and how it looks like and all. But then before that, let me talk a little about the stability of a system. You consider a potential drawn like this, okay? Okay, something like this. Now you can say that I have a ball here, okay? Now if I give an infinitesimal or if I give a displacement to the ball, I can say that the ball may, depending upon the energy I give, okay? So the ball may sometime go like this, but then since the potential well is quite deeper, you can say that the ball will come back, right? And if you go like this, it will come back. So you have to give that much potential to actually overcome the, or that much energy to overcome this potential. There is a very big barrier here, right? So I can say that this ball here, when you move it or when you give a small displacement, an infinitesimal displacement, I say, when you give a small perturbation, actually it will go and come back to the same position. And we can call this as a stable point because, as I said before, the ball will come back to the same position, to the well. So this I can consider as a stable point. Now you consider the ball here, right? So what happens here? It is now staying there, but if you give a small push, so that if I give a small push this way, obviously it will roll from here and come and stay in another well, right? So let me call this as the V3 or this is the point as 2, this as 1. Okay, so you can say that the if you give it in this displacement for the ball at the point say 2, it will, if I give the displacement this way, it will come and stay in this the third well, or if I give a displacement in this direction, obviously it will come and stay in the first point. So I can see that a small perturbation will actually affect the system such that it will not come back to the original position. So we can call this as an unstable point. So, okay. So this is another unstable equilibrium point. So I think this is what we have studied in the simple pendulum case also. So this was explained there also, but then a little more detailed explanation. Now you can see that here 3 is also a point like this, but then not that much deep as the point 1. So it means if you give a little more displacement, it may go back. But then it is, you can see that the point is a different point. You can, if you give, even if you give a potential, it may go, give energy, it may go, but again it will come back and stay in this particular well. But if you give a potential, or if you give an energy in this direction, or displacement in this direction, it will go, it may actually pass this potential, overcome this potential, and come back and stay in, not come back, it will come and stay in this potential well. So all depends upon how the system is at the beginning, or how the system is at the equilibrium point. So depending upon the various cases, the points, or depending upon the situation, actually we can say that actually the system changes accordingly from where the system, or in the initial system is, or how you're going to, or how much energy you're going to give. Anyway, we can call this 1 and 3 as stable equilibrium points, and this 2 is obviously an unstable point. Okay, so now this is a little introduction which I am giving regarding the stability part. Now we are going to analyze how you can plot the trajectories for different various systems. Okay, so now you consider, you're going to learn about stability metrics. Okay, about the stability metrics. So for that, first I'm consider general equation of a system. So let me write the general equation of the system as x dot. That is, we know that x is, we write the equation of motion in terms of x or y, right? But then when we say the displacement, we can say that I can take the first derivative of the x, right? That is how you determine the evolution of the x, or evolution of the system with respect to time. So for that, I first order derivative, I can write x dot. Let that be a function of x and y. Okay. Now let me take another system, or the y displacement in the y direction, that is dy by dt, and let that be of the form of another function, say x and y, g of xy. Okay, and this f and g are some non-linear functions. Okay, f and g are some non-linear functions of f of x and g of xy. F of xy and g of xy are non-linear functions of, say, x and y. Okay, now let me say that at the fixed point, let me call these fixed points as say x0 and y0, and we can say that this is one equilibrium point, such that I say, so let x0 and y0 be one equilibrium point, that is when the system are staying there for a long time. Okay, so let x0 and y0 be an equilibrium point, or a fixed point, then at that fixed point I can say the time derivative is 0, right? So that means I can write at that fixed point x dot and y dot as 0, or then I can write at f of, so at that fixed point means x and y is x0 and y0, so this is equal to 0, and g of x0 and y0, and that is equal to 0, right? Okay. So now how many such fixed points are there for a system? That all depends upon how the function is. So I suppose here you say I have a function is a function like this, then I can say there are two fixed points or two stable points, right? So that depends upon what is the form of the function. Okay. Now, now the stability of these fixed points that we can understand by considering or giving a small displacement. Okay, so how we can, I said, so whether this is a stable point or not, or how much is the stability, that you can understand by giving a small displacement. So if I give a displacement, when it comes back to the original point, we say that is a stable point, right? So how to determine the stability of a fixed point, you can actually give a small time evolution for the system and find out. So in that process here, what I'm going to do is I'm going to give a small displacement to the x and y. Okay. Now, as per Taylor expansion, the time evolution of this displacement, delta x and delta y are the displacement. The time evolution of the displacements can be written as delta x dot time elevation of displacement is derivative of function x with respect to x, that is I am writing as f of x, x0, y0, delta x, that is the displacement delta x, plus derivative of this function with respect to y, that is fy, x0, y0, okay, delta y. So this is the Taylor series expansion. Okay, or we only assume two terms because actually all the other nonlinear terms or second order terms we have actually excluded. So we linearize the time evolution of, our plan is to linearize the time evolution of this displacement. So in that process, the higher order terms are neglected in the Taylor series expansion. Okay, so then delta y dot can be written as g of x, then similarly as we have written the previous case x0 y0 delta y, sorry, that is since it is in terms of x, it is delta x itself, so delta x plus then g of y, okay, then x0 y0 on delta y. Okay, so this is the Taylor series expansion. Okay, now this expansion can be written in this form as well, right? If I'm going to write in the matrix form, I can write this as by dt of delta x delta y, right? Column matrix delta x and delta y, and again a matrix which is fx, which is x0 y0, then fy x0 y0, then this one g of x x0 y0, then g of y x0 y0, okay, that, and then delta x column matrix delta x and delta y. Okay, so this is actually a linearized equation, and we have written that in terms of a stability matrix, and I call this M as the stability matrix. Okay, I call this matrix as M, and this is actually referred as the stability matrix. And if I solve this, this is a eigenvalue equation. I can write this as mx is equal to, I can write x is equal to lambda x. I can write this in this way. So this is actually similar to an eigenvalue equation. And while solving this, I get, let me say that lambda 1 and lambda 2. Sorry, this is wrong. Lambda 1 and lambda 2 be the two eigenvalues of this matrix M. And the corresponding eigenvectors are d1 and d2. Okay, so here let lambda 1 and lambda 2 be the eigenvalues of this equation, and the corresponding eigenvectors are d1 and d2. And you can solve this equation by finding the solution for determinant. You know the determinant m minus lambda I equal to 0. Okay, so lambda 1, I have m minus lambda 1 into I equal to 0. Then you can solve for the delta x and delta y. Similarly, for lambda 2, also if you put it in, then putting lambda 2 here, then solving again, you will get another delta x and delta y. Okay, so thus by solving this, finding the determinant of m minus lambda I, or solving, you can get the expression, or they can get the solution for delta x and delta y. Now the solution for this delta x and delta y, let me call this as the x, that is this capital X is actually the column vector formed by small delta x and delta y. Okay, this capital delta X is actually the column vector formed by delta x and delta y. So this solution I can write in terms as C1 in the general solution is C1 into D1. D1 is the column vector corresponding to that, D1 e raised to lambda 1 into T, okay, plus C2 into D2 e raised to lambda 2 into T. So the solution for delta x and delta y is C1, which is a On's coefficient, into d1, this is the column vector, and e raised corresponding to lambda 1, e raised to lambda 1 into t. And here you can see that this solution of x is actually an exponential function, right? So which I mean by saying that when you have the lambda 1 as positive, so you lambda 1 and lambda 2 can have positive and negative values while solving depending upon the different systems. So for some systems I can get the solution for x as a decaying function depending upon lambda 1 negative or positive. So if lambda 1 or lambda 2 is negative, I can say the system decays because exponentially decaying. Or if lambda 1 is a positive value or lambda 2 is positive, I can say that it is actually a progressive one, not an exponentially decaying or exponentially growing function. So now depending upon the values of this lambda 1, lambda 2, I can have different solutions for this x and y. And depending upon these values of lambda 1 and lambda 2, whether they are real or imaginary, or whether they are actually negative or positive, actually our stable points, or whether the fixed point are unstable point or stable point, or how they are actually moving, whether they are actually the face portraits, whether they are straight lines, or whether they are spiral points, spiral type of face curves, or whether they are the ellipsoid, whether they are hyperbolic, everything can be found out. So our next thing is we are going to classify the fixed points depending upon the values of this lambda 1 and lambda 2. Okay, so I hope you understood this much. So thank you. The next session you will understand how you classify the fixed points. Thank you very much.